So fusion then is the, yeah,
You up for saying that?
sure.
For us,
Oh, did I not put that in? Oh, sorry. The nucleus absorbs the neutron and forms a highly unstable isotope that breaks up almost instantaneously. So this, when it's talking about the highly unstable isotope, it's that. Okay? It's like the transition state almost kind of thing. You want to think about it like that. So then fusion is the combining so think fusion is fusing together, combining of small atomic nuclei to make a heavier, more stable element. Massive amounts of energy are released, even more than in fission. So even though fission releases a lot of energy, this releases more. This reaction is the driving force behind the stars and sun. Or behind the sun, which is a type of star. So let's write out the formula for this example. Now when it says deuterium isotope, that means a hydrogen that has 2 as its mass number. So it's just the same, it's the same thing that I was showing you earlier. So here we have H2, and tritium means a hydrogen isotope with 3. Okay. So there's a neutron release, as it shows us, and helium is produced. So when we look at our conservation,
Are those helium or hydrogen?
oh yeah, helium, sorry, He. Thank you.
What about the other two?
Those are hydrogen, yeah. Because the proton is 1. So conservation of nucleons. On this side we have 5, and on this side we have 5. So that's good. And then conservation of charge. Here we have 2, and here we have 2. So that's good. Now, however, just an observation to make. Just because our conservation of nucleons and our conservation of charge stayed the same, like that's all good, our laws work. But notice that the daughter element, okay, if we didn't look at the nitrogen, the daughter element, like what's left over, like what you can take, okay, tangibly, because the neutron is like shot off into space, released as energy.
Neutron, not nitrogen.
I said nitrogen? Oh my gosh. Okay. Yes, thanks. The neutron is like shot off into space, it's released as energy. So what we have left over is less than what we started with if we don't think about the neutron. And so I'll talk about it more in our next lesson, but that's the whole mass defect equivalence theory it's called. And so we'll do that later, but that's Einstein's law. So now let's do our nuclear fusion. So fusion is the fusing or combining of 2 or more lighter elements into a larger one. Let's notice that too. These ones are like small atoms combining, and this one is a large atom combining. That's another big difference too. So this one, small things coming together, big things splitting apart. High density and high temperature environment is required. A high density is required, so high probability, small particles will collide and fuse together. So if you want it to be all packed tight together so that the particles are moving around and there's more probability that they bounce off or bounce and hit each other so that there's that actual fusion. There is an extremely high energy is required to bring 2 or more protons close enough and overcome the electrostatic repulsion. Okay? So think about bringing 2, say, north ends of a magnet together. It's kind of the same like that, right? Thinking back to our fields and forces. Like fields will want to repel each other. So protons are both really positively charged. So if we want to take 2 nuclei together, combine them, that's a lot of repulsion. So you need a lot of energy to push them together. That's why the larger the nucleus, the more it won't work, right? So if you have like big nuclei coming together, there's too much repulsion. You can't force them together as much, okay? So small. You need the small ones to come together. And even then, it's a lot of energy to push them together because they don't want to hang out, okay? The energy released by fusion is 3 to 4 times greater than fission. So both are huge, much more amounts of energy released than just normal chemical reactions, though. This is not a chemical reaction, it's a nuclear reaction. Fusion occurs in stars, such as our sun. And few radioactive particles are produced from fusion. So that's the main lesson. So now answer the practice problem. Explain why only relatively small nuclei can undergo fusion. That's what I was just talking about.